friends and students, welcome to today's session on design of knuckle joint. Learning objective of the today's session, design a knuckle joint. After this session, you will be able to design a knuckle joint. You will find knuckle joints which are used in many applications. Look at the figure, you will find this is one of the application in to connect this trolley with the tractor. Now here you will find is a tractor part, or you can say the eye, then it's a fork which is a part of trolley, and it's a pin. Again there is a hole to insert here a split pin or other pin to lock it properly. Again you will find what do you mean by knuckle joint and where knuckle joints are used. The knuckle joint is used to connect two rods whose axes either coincide or intersects or lie in one plane. Why intersects or lie in one plane? Sometimes it may be coincide, sometimes it permits certain angular moments between these rods. Look at this. This part which is shown by here, the green color, it's a fork. This part is a eye and pin is inserted here to fit it properly. This eye and fork, and here provision is made to lock it this pin properly. Split pin may be used here, and because of that you will find there may be the angular moment is possible of this fork as well as the eye also. It permits certain angular moment between the rods. Again this is the end rod of the fork, this is the end rod of the eye having same diameter. Then this is the enlarged portion of the fork, this is the enlarged portion of the eye, and then thickness of this the here fork, then the thickness of the eye, and again here thickness of the eye of the fork. Again this is pin here which is inserted, it's a pin diameter that is small d. Again where these knuckle joints are used, you will find knuckle joints are used, or you can say the joint in between the tie bar in rope trusses, then joint between the links of suspension bridge, then joint between the link of the bicycle chain, then joint between the fulcrum of levers, joint between valve mechanism of reciprocating engine, or in many applications you will find knuckle joints are used. Different elements of knuckle joint. Knuckle joint consists of three elements. One is this component is the eye, second one is the pin, and third one is the fork. Look at the construction of the fork. You will find fork consists of two eye. This is single eye and another eye. It consists of two eye. Again here this eye is inserted here, and pin is inserted through this eye of the fork, then eye, then bottom eye of the fork, and here it is fitted or locked properly. It's about the knuckle joint construction and components. Again here you will find in many applications in agriculture, farm equipments also this the knuckle joints are used. You find this hydraulic system where this part is a fork, this part is a eye, and it's a knuckle pin. Again here in other agriculture equipments also you will find the knuckle joint. Again it's a fork, it's a eye, and then it's a pin. In many applications, look at this here in brake lever of the bike or two-wheeler you will find application, then suspension system, it's a eye, then it's a fork, then it's a pin. Even though in specs also at the hinge you will find it's a knuckle joint. Many applications you will find knuckle joint. Now let us see what are the advantages of knuckle joint compared with the other simple machine elements such as quarter joint. The knuckle joint offers the advantages. Its design is very simple. It consists of few parts, that's why manufacturing is also simple. Then assembly and disassembly or dismantling of the parts of knuckle joint is quick and simple. Just we have to remove that split pin, and we can easily take out the knuckle pin out from eye and the fork. Now look at this. That means knuckle joint consists of three parts. One is the eye, second one is the fork, third one is the pin. In design of knuckle joint, what you have to do, we have to find out the dimension of this end rod. This is end rod diameter, that is denoted by capital D. This is the enlarged portion of the eye. This is enlarged diameter of or portion of the eye, and this is enlarged portion of the fork. This component is the fork, but fork consists of the single eye and another one, that means two eye. This is the diameter of the pin. Here this is the head diameter of the pin. Try to understand. And again here this portion is known as the outer diameter of the fork, and this portion is known as the outer diameter of the eye. We are going to use the nomenclature in here design. Look at this figure, you will get the idea. Now it's a sectional front view, it's a top view. Here you will get this component is the fork, this component is the eye, pin is inserted here, and again here split pin is also shown in the diagram. Now let us consider here this knuckle joint is subjected to force P, axial tensile force, that is P. Then second, you will find this is end rod of the fork and this is end rod of the torque, which is shown here. Look at the end rod A and end rod B. The end rod of the fork and end rod of the eye. The dimensions nomenclature which is used, that is capital D for the end rod. Again here this part is a enlarged portion of the fork, and here you will find here it's a enlarged portion of the eye. Look at this enlarged portion of the eye and fork, which is denoted by capital D suffix 1 here, this value D1. Then here small d is the pin diameter, knuckle pin diameter. Look at this. Then small d1 is the head pin diameter. Then small do is the suffix. Here you will find outer diameter of the fork as well as outer diameter of the eye. Try to understand. Then b is the thickness of the eye, small a is the eye thickness of the fork, and small a again here bottom, eye thickness of the fork. So you can say it's a fork thickness of upper eye A, fork thickness at lower eye, that is small a, and here it's B. That means fork consists of two eye. Try to understand. This is about the nomenclature. And I have also here mentioned the capital D is the diameter of each rod, capital D1 enlarged diameter of each rod, small d is the diameter of the knuckle pin, do is the outside diameter of the eye or fork, small a is the thickness of each eye of the fork, b is the thickness of eye end of rod, d1 diameter of the pin head, and x distance of the center of the fork radius r from the eye. Here this x which is shown here. Look at this diagram. This is x. This is the center of the fork from this component is eye. Again here as per the nomenclature, once I would like to revise here. This is capital D end rod diameter of the fork and end diameter of the eye. That means capital D end rod diameters are same for fork as well as the eye. Then enlarged diameter of the fork and enlarged diameter of the eye, which is also same, that is capital D1. Then here pin diameter again small d, pin head diameter small d1 is the suffix, and outer diameter of the eye as well as the fork do. Then thickness of the eye small b, and thickness of the fork, that is b. This nomenclature we are going to use in our design. How to design the components? Components means eye, fork and pin. Again here first of all find out the end rod diameter of the eye and fork. You can consider anyone, no problem. Now I am considering in this case the eye is considered. Look at this is the eye which is subjected to tensile force. So because of this tensile force, what is going to happen? Tensile stresses are going to induce, that is sigma t is equal to P by area. But what is the area? Again this end rod is having circular cross section. So when we are going to consider this cross section, you will get area pi by 4 into d square. So what is the tensile stress? Sigma t is equal to P upon pi by 4 into d square. By using this sigma t permissible from the material which is used for the eye end rod, you can easily find out the capital D, that is end rod diameter. Once you will get the end rod diameter of the eye or a fork, which is same for both, so what you have to do, find out the LR diameter. In this case it's shown square, but generally if it's a circular one, so you can find out capital D1 is equal to 1.1 times capital D. That means end rod diameter multiplied by 1.1, you will get this LR diameter of the eye and LR diameter of the fork also. Try to understand by using empirical relation. Now next, now eye as well as the fork. Three simple stresses are going to induce in it because of this tensile axial force. Because knuckle joint is subjected to or it transmits only axial tensile force, and because of this tensile stress, direct shear stress, and crushing stress, which are going to induce in eye as well as the fork, and we are going to find out these induced stresses in fork as well as the eye. If these induced stresses are less than the permissible stresses, we can say our design is safe. Try to understand. Now let us see first element is the eye. Now here, look at this. When it is subjected to tensile axial force P, what would happen? You will find tensile stresses are going to induce in it. Always consider the weakest cross-sectional area, because to here the end of the eye here hole is provided to insert that pin. This section is the material is removed, means weakest section, and it is going to the fail because of this tensile load, and that's why we are going to consider this weakest section. And if after taking the cut, you will get the cross section like this. Again here thickness of the eye is B, outside diameter of the eye is DO, and inside diameter, that is diameter of the pin here, small d. So how to find out this cross sectional area? You will get this DO minus this is D. This area is, that means you will get this dimension multiplied by B. So you will get cross sectional area is equal to B in bracket DO minus D. And therefore tensile stress induced in the eye is equal to axial tensile force P upon this area. By using this expression, what you will get? You will get tensile stress induced in the eye. You can check it whether this tensile stress is less than the permissible tensile stress. Permissible means from the material, by using FOS you can find out permissible allowable, and this induced stress should be less than this. You can say your design is safe. But the interesting thing here, to find out the sigma t, what is the requirement? You should know the small d, small do, and b. And where you will get this small d? So you will get small d from the failure of the pin, because knuckle pin is going to fail because shear failure as well as the bending failure, from which we are going to calculate small d. And once you will get the small d, by using empirical relation you will get the do, and even though B also is having the empirical relation with the capital D, that is end rod. I will explain that later on. Then next failure of the eye, that is shear failure. So what is happening because of this tensile axial force, the shear failure of the eye which is going to occur here. Look at this. This is the shear area. The area of each plane which raises the shear failure, because shear failure of the eye which is going to occur in two planes, this plane top side and bottom side. Look at this bottom side shearing which is occur here, top as well as the bottom. So we have to consider two shear areas. So now here area of each plane, how to find out? I have shown here this is B. Again we have to find out this distance. How we will get this distance? Total outer DO minus inside diameter, that is D, and or half portion by 2. The B multiplied by this DO minus D by 2, you will get this. This is the area of each plane resisting the shear failure. But here how many shear areas? 2 areas. We have to consider 2. That's why total area multiplied by this 2, you will get this is the total area. And therefore simple equation tau is equal to P by A. Substitute this total area, so you will get this equation. By using this equation you can find out shear stress induced in the eye and check it whether this induced stress is less than the permissible. Then you can see your design is safe. Now third failure of the eye, that is crushing failure. What is happening when this knuckle pin is properly fitted? And I have already told, when you are going to say crushing stress, when there is no relative motion between the two meeting parts. That time what would happen here? How to find out the crushing stress? Sigma c is equal to P upon projected area. But here because of the pin, what is the projected area which is shown here? Look at this. So this is the B, and again this is the small d. So what is the projected area? Small b into d. So therefore crushing stress induced in eye because of this pin here, that is sigma c is equal to P by BD. By using this expression we can find out the crushing stress induced in it. You can check it. This crushing stress should be less than the permissible or allowable crushing stress or compressive stress. Now let us see the another part, that is fork. Same way like a eye, again fork is going to subject, because this axial tensile force, again say we have to find out the tensile stresses induced in it, because it is going to fail against this. The tensile failure of the fork, that we have to check. How to find out tensile stresses induced in it? Sigma T is equal to P by area. But look at this. Again consider the area of the weakest section, and where we will get at the pinhole again. But in this case, this fork consists of two eye. This is one eye and this is second eye. That means this area, again bottom, these total four areas that you have to consider: 1 2 3 4. How to find out this? The area of this weakest section, total outer diameter is small do, inside is small d, then thickness of this eye of fork, bottom as well as the top, which is small a. Here it is mentioned. Therefore the area of this weakest section is equal to actually A into this do minus d. But here this is also the top eye and in bottom eye, that's why multiplied by 2. Therefore A 2 into A in bracket do minus d. So you will get tensile stress induced in the fork P upon this area of the weakest section that we have to consider. And you can check this induced tensile stresses should be less than the permissible stresses for the fork. Then second case, shear failure of the fork. Now here again, because of this tensile axial force, shear failure of the fork, which is going to occur at this, the hole here. And because of this, but the what is happening, shear area of one side here you will get, as well as the bottom, that means 4 here you will get shear failure of the fork, which is going to in top eye as well as the bottom eye. Top eye you will get the 2 shear areas, and here 2, total 4. Therefore first of all find out the shear area of each plane. Look at this, here it is mentioned here at the total here this thickness is A, because of the pin here diameter is D, outer diameter is DO. You can see in this way, DO outer diameter, inside D, and this is A. So what you will get, shear area of one side for one end is equal to DO minus the small d by 2 and multiplied by thickness A. This is for the one shear area plane. Then there are total 4, 1 top, bottom 2, third here top, again bottom 4, then total 4 area. Then multiplied by 4 you will get the total failure area 2A multiplied by 4. The 2 1s are 2, 2 2s are, so you will get 2A in bracket do minus d. So you can use this area. The tau shear stress induced in fork is equal to P upon 2A in bracket this area. Important thing, how to consider the area, that is important in case of simple design, simple machine components. Tau is equal to P by this total failure area. So you will get tau induced in this, or shear stress induced in the fork. You can check this induced stress is less than the permissible. Then third one is the crushing failure of the fork. Again, if this pin is properly fitted, there is no relative moment, you will find crushing stresses are going to induce in it. And again we have to consider the projected area, the contact between the pin and the fork. Again fork consists of two eye, this and this. That means we have to consider this part or projected area of this top eye and projected area of the bottom eye of the fork. And therefore how to find out this projected area? Again you will get crushing area. Here A is the thickness of the top eye of the fork, A is the thickness of the eye of the bottom side eye of the fork. Therefore you will get A into this small d is the area of one eye of the fork. Therefore total eye for the fork, therefore 2 times A into d. The crushing area sigma is equal to P upon 2 times A into d. Try to understand. Again here what you have to do, this is about the crushing stress. The crushing stress induced you will get from this equation. You can check it whether it's within permissible limit or not. If it is less than the allowable, you can see your design is safe. But here in all these equations of the fork and eye, you will find the small d, small do, and other parameter, that is small a and small b, are there. And how to take the values of small a, small b, small d and d1. But here so you will find a and b we can easily calculate from the, if we know the end rod diameter, that is capital D. The A is equal to thickness of the eye of the fork, that is 0.75 into capital D is the end rod diameter. Then B is the thickness of the eye. B is the thickness of the eye, and which is equal to 1.25 times the D. D is the end rod diameter. We can easily find out the tensile failure of the end rod of the fork or a eye by using simple equation. So you will get A and B. Once you know the A and B, you can easily find other dimensions. But to find out the other stresses induced in the eye and the fork, small d is the requirement. But where will get the value of small d? For that purpose, you have to design the knuckle pin against shear failure and bending failure. Try to understand. Once you know the D, then and then you will get the pin head diameter is equal to 1.5 times the D. That means to design a knuckle joint, the important requirement is first of all you should know the capital D. Once you know the capital D, you can easily find out the LR diameter, that is D1, 1.1 times capital D. Then you will get the value of A and B. Small a and B means thickness of the eye of the fork, and B is the thickness of the eye. Then D is required. Small d means pin diameter is required. Now let us see how to find out the small d. For that purpose, we are going to consider the design of pin. Now pin is also going to fail against shear. Look at this. This is the pin subjected here. This side. This is the fork. This side is the eye. And because of when it is subjected to tensile axial force, what is happening in two areas here? Top plane as well as the bottom. Shear failure of the or shifting here displacement. Or you can say here sliding. The shear failure of the pin which is going to occur at the top as well as the bottom in two planes. Now here is the how to consider the cross section. You will find if you are going to observe it circular one. The area of each shear plane is equal to pi by 4 into d square, and bottom area is also pi by 4 into d square. That means shear stress induced in the pin is equal to tau is equal to P upon area. But here two shear areas, the multiplied by 2. Here look at this. Therefore shear stress induced in the pin is equal to P by 2 in bracket pi by 4 into d square here. Try to understand. And why 2? Two shear areas. 1 and this 2. Double shear. And you will get, by using, you can rearrange the equation, you will get small d is equal to this equation. By using this equation, you can find out easily small d. Then is going to fail because of bending. Why bending? When pin is tight, failure occurs due to shear only. But sometimes during operation there may be possibility of loosening of the pin, and when the pin is loose, it is subjected to bending moment. How to consider this? Look at this. This is the the fork side. This is the eye side. You will find here it is assumed this towards the eye side. The load which is acting on the pin is uniformly distributed, but for the fork side it's a uniformly varying load. Uniformly varying load. We will see this analysis in another year. Look at this here. In this diagram I would like to show it's a pin. It's a uniformly distributed load because of this eye, and here varying load or triangular load at the eye of the the fork, top as well as the bottom eye of the fork. Again here, how much is the thickness of the eye? That is B. Here it is mentioned B. And what is the thickness of the eye of the fork? It's A, and this distance is also A, and it's a triangular load. To convert this uniformly distributed load into point load, so you will get P by 2 here, P by 2, and divide this B into 4 parts. So you will get P by 2, which is going to act from this side at the B by 4, and this side also B by 4. That means at the middle B by 2, B by 2, again here B by 4, B by 4. In this way, again this triangular force which is going to act from this side 1/3 of the A, or from this side 2/3 of the A. Now let us see here in this diagram. You will find here the uniformly distributed load is converted to point load B by 4. Here also B by 4. Then again this the triangular load is also converted into point load. From this side 1/3. That's why A by 3. And from this side 2 by 3A. 2A by 3, or 2 3 into A. Again after that, what you have to do? So we have to find out the bending moment, to find out the bending stresses induced in it. We know that the simple equation sigma b is equal to mby by I. So how to find out the mb means bending moment. The bending moment is maximum at the center, and therefore what we have to do? Find out the bending moment. Consider from this side p by 2 into this distance. This distance means a by 3 plus this b by 2. So I have written here mb is equal to p by 2 in bracket this distance a by 3 plus this distance, that is b. This total distance is total is the b means b by 2. That's why b by 2. And here This is opposite to this p by 2 minus p by 2. That's why minus p by 2 into this distance. This distance means b by 4. Here it is mentioned. Then again what you have to do, take p by 2 common outside. What is remaining inside? A by 3 plus b by 2 minus b by 4, bracket complete. And now here b by 2 minus b by 4, you can multiply it here. So 4b minus 2b upon 8. The 4b minus 2b means 2b by 8 here remaining. And again you can arrange the terms. You will get mb is equal to p by 2 in bracket b by 4 plus a by 3 here. Then what you have to do, once you know the bending moment, what you have to do, use the simple equation sigma b is equal to mb by I. The substitute this value of mb here. Y means d by 2 because pin diameter, that is circular cross section. So what is y? That is d by 2. And then I moment of inertia, that is pi by 64 into d raised to 4 for a circular cross section. Substituting all these values, you will get sigma b here. So what you have to do, by using this expression also, you can easily put b and a by using empirical relation, find out the small d. That means by considering the bending failure and by considering the shear failure, find out the small d or diameter of the pin. And after that, what you have to do, you have to check whichever is the larger diameter of the pin that you can consider in your design. This is one thing. Second thing, another approach you can use it, you can find out the pin diameter by using the shear failure and substitute in this equation, find out the bending stress induced and check it, this bending stress is less than the permissible. This is also the correct one, no problem. This is about, that means by considering the failure of the pin against the shear as well as the bending, you will get the pin diameter, and then we can easily find out the pin head diameter, that is multiplied by using the empirical relation I have mentioned, 1.5 into small d pin diameter, you will get the small d1. That means to design a knuckle joint, you should know the capital D and or diameter. Then you should know the DO, annular diameter, that is 1.1 times D. Then you can easily find out the small d from design of the pin. Then small a, small b by using empirical relation in terms of capital D, and the pin head diameter, that is 1.5 times the small d. And what's about the other relations? And you can check the fork as well as the eye for the different stresses induced in it by using the simple equations. Tensile stress induced in the fork, tensile stress induced in the eye. Shear stress induced in the fork, shear stress induced in the eye. Crushing stress induced in the fork, crushing stress induced in the eye. And all these induced stresses should be less than the permissible and allowable. Then and then you can see your design is safe. This is about the knuckle joint. Thank you. I hope you understood the design of knuckle joint. I have referred V. Bandari's book, Design of Machine Element, McGraw-Hill publication. Thank you. If you have any query, please contact me at 9890426679 or mail me at pbkushare@kkwork.edu.in.